Hi, welcome to the next of our series, Practical Electromagnetics for Engineers. In the last video lecture we learned about potential. This time we'd like to explore more the relationship between the potential and electric field. So we've learned that charges create both scalar fields, which we call potential here, and vector fields, which we call the electric field, which is the invisible force rays that push on charges. And we know if we have a charge Q sub A creating an electric field, the force on another charge, we'll call it Q sub B, is just equal to the charge times the electric field created by A. Similarly, if charge QB is in the scalar field, the voltage produced by charge QA, and so let's write an A to make sure we're talking about the same charge here, we know the energy, and let's call it U because E gets confusing, is essentially equal to the voltage times the charge QB. I've located Q sub A right here at the center, so let's draw a line here and say that that point right at the center is the position of Q sub A. And I've used MATLAB to plot both the electric field, that's these black arrows, the vector field, at every position in space, but also I've done a contour line, and you're probably familiar with contour lines for maps, where each of these lines represents a constant potential, and these lines represent the value of the potential again at every point in space. You'll notice a couple of relations between the arrows, the electric field, vector field, and the potential, the scalar field. It looks like the scalar field is always perpendicular to the electric field. And this actually kind of makes sense, because you'd expect that potential energy to decrease as the square as you go out radially any distance. So let's explore these relationships more, and in order to do this we're going to have to revisit the exploration we did in the last video of moving a charge along the x-axis and trying to calculate the potential energy, but let's do it in an actual vector field created by a distribution of charges rather than just a single charge, to look at a general case. So here I've plotted the vector field from a single charge, again Q sub A at the origin. It's given by this expression, and what I'm going to do is I'm going to take some other charge, my little Q sub B, and I'm going to move it from point 1 all the way to point 2 over here, and I want to know what the change in potential energy is, or the difference in potential, the voltage between point 1 and point 2, as we would call it in electrical engineering. And in order to calculate this, what I'm going to do is, instead of sort of doing the integral, I'm going to have to figure out how much energy I need as I move these little red arrow segments through the field step by step. And essentially what I'm going to do is I'm going to call those red arrow segments the vector dl, because they actually have a direction to them, and they're sort of a tiny little incremental length. And you can see where this is going. When I label anything delta, we're going to have to do some calculus later. But let's take a look at this first. So what we want to do is we want to think about the coordinate frame of these arrows. And you'll notice that the vector field essentially is going in this direction, so it has a component that's pushing against the arrow, and it has a component that's pushing orthogonal to the arrow. It turns out that anything that's pushing orthogonal to the direction that arrow is going doesn't change the energy, because it's pushing sideways. The energy we have to fight against is essentially what's pushing against it. So we're doing some energy to move this arrow forward. If we move the arrow a little space and sum up all the energy, and again look in the coordinate frame of the arrow, again what we see now is there's more of the electric field pointing orthogonal to it and less pointing against it. It's getting easier. As we move further along, all of the electric field is going orthogonal to the arrow, it's taking us no potential energy or no energy to push this thing along. And if we take one more step and go further, you'll see that now actually it's like we've got a tailwind pushing us along. We've got a component of the electric field that's orthogonal, but we've also got a component that's pushing the arrow along. So now we're moving down the potential energy curve. We're dropping in energy. So essentially what we're doing as we move here is we're going up, 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 up in energy until we're orthogonal. At this point we have the highest energy or the highest potential along this path, and then we're going to drop back down in potential as we get to point 2. So how do we do this? Well, in order to do this, we find that essentially what we need to do is we need to multiply two vectors, because we've got our little length dl that's pointing along the direction of the line, and so that's basically vector dl. But we want to know the component of the other electric field E that's pointing along dl or pointing against dl. We don't care about the component that's orthogonal to dl. And this requires that we learn how to multiply vectors. So let's do that next. It turns out that there are three ways that you can multiply vectors. You can multiply a scalar by a vector. You can multiply a vector times a vector to give you a scalar. And you can multiply a vector times a vector to give you another vector. And we're not going to consider vector times vector equals vector yet. We'll get to that later. But we do want to learn about scalar multiplication and multiplying two vectors to give a scalar, which is something we call the dot product. The scalar multiplication is pretty easy. Here we have a vector. Let's call this vector A to match with my notation over here. And if we multiply this vector A times B, essentially all we do is increase the length of A. So essentially if B is equal to something like 1.5, the new vector A is going to point in exactly the same direction and be about 1.5 times the length. And if you want to do it more mathematically, you just multiply that scalar by each of the three components of the vectors. That's pretty trivial. What we want to do, though, in our problem of basically going from an electric field to calculating a potential is multiply two vectors together and get a scalar. Because remember, our little line segments are a vector, our electric field is a vector, but we need to get a scalar up because the potential is a scalar out of this. And we do this using something called the dot product. And essentially what we want to know is we want to know the length of this vector B along the vector A. And essentially the way we do that is we have vector A, we have vector B, and when we take the dot product, we just multiply the x components together, multiply the y components together, multiply the z components together, and then just add each of those up, and this is going to give you a scalar number. And essentially what this does is it is essentially the projection, as they call it, of B along A, multiplied by the length of B and length of A. There are various ways you can express this. You'll see this in various books. But generally what happens is if B and A, let's draw A to be a different length here just to be a little bit more consistent. If B and A are pointing in the same direction, then A dot B is just equal to the magnitude of A times the magnitude of B. If B and A are in orthogonal directions, so A's that way and B's at 90 degrees to it in some coordinate system in space, then the dot product is equal to 0. So in this case, A dot B is equal to 0, as you'd expect, because there's no length of B along A, because that's what orthogonality means, as we saw previously. In the more general case, as I've drawn right here, and there's some angle theta between B and A, then A dot B can be represented as the length of A multiplied by the length of B. Again, I'm using the magnitude symbols for the length, times the cosine of theta, because when theta is 0, the cosine is equal to 1. But really, this is the best expression right here to calculate dot product. Now that we know how to multiply two vectors together and get a scalar using the dot product, we basically are able to convert from electric fields to potentials. There are three different cases we want to consider of converting from electric field to potential. The first case is we want to know the potential difference between 2 points, point A and point B. This is the example we did earlier. In this case, essentially what we do is we just integrate the component of E that lies along each little segment of the line that goes from point A to point B. And that's going to give us the potential difference between 2 points, points A and point B. We may also want to know what the potential difference is at any point in space. In this case, we have to go out to either positive or negative infinity, where we've defined our potential to be 0, where we're so far away the electric field doesn't push another test charge at all, and essentially go along some path and integrate to the point P, which is represented by this vector r sub m that we're interested in calculating. Again, all we do is we basically say we want the component of the electric field that lies along each path we take. The third thing we may want to do is we may want to go around a loop, and in this case what we're going to find is that if we go around any closed loop, we find that the potential around a closed loop is 0, and you know this from electrical engineering. This is sort of, Kirchhoff's law and things like that. But now we're representing it in the most general case we possibly can. So let's go and look at each of these cases individually. So here's the first case where I want to calculate the potential difference between 2 points. So let's set basically a point here and call it point A, and let's randomly choose a point over here in coordinate space and call it point B. I've graphed using MATLAB just a random electric field. This is a much more complicated electric field distribution, a much more complicated vector field than just the point charge. And it doesn't really matter how the arrows go, but we just know our electric field is given by a vector at every single point in space, because that's the definition. So essentially what we can do is we can just draw a line between point A and point B, and in order to calculate the potential difference, we just take each segment of that line, which we know is a vector, so this vector is going to point in that direction, and we just basically take the dot product of this little segment of line and the electric field, which we know is going in that way at that point in space, put it in our little bin, go along to the next segment, do the same calculation, taking the electric field vector and the dot product, which gives us a number, add it up, because all that's happening with an integral is we're just adding lots and lots of little tiny segments, and I just move along my line, arrow by arrow by arrow, dl vector by dl vector, until I get to point B, and the sum of all of those things is going to give me the potential difference between point A and point B. Now, why did I draw a straight line? It turns out that I don't have to go along a straight line. I can actually choose any path. If I wanted to have a path that went like this from point A to point B, I could do exactly the same calculation and I would get exactly the same number, because the potential difference between any 2 points in space is going to be constant no matter how I got there. I could wiggle around like this, come up here, do a loop, and come back, and even if I took that path, I'm going to get exactly the same number. The potential difference between any 2 points in space that has an electric field in it is the same no matter the path I use to go from point A to point B. This can be useful sometimes because you can choose a path that makes it the easiest for you to calculate this if you're ever required to do so. Another problem we posed ourselves was essentially going out from infinity and calculating what the actual value of the potential was at any point in space where we want to measure it. So let's choose our point and have our vector r sub m go out to some point in space. This problem is not very often done, because instead of basically giving you the electric field distribution over the box that I have here, we'd have to know it everywhere in space, but the idea is exactly the same. We just basically choose somewhere out at infinity and then can plot any path no matter what we want to end up at r sub m. Exactly the same idea. It doesn't matter if I go and start at basically infinity out here and come in a straight line, or infinity and come in a straight line out here. As long as I start far enough away, any path I choose that ends at the point given by this vector r sub m is going to give me the value of the potential there. One of the famous cases in electromagnetic, and something you should just sort of move to memory is that if I go around a loop, let's say I start at point P, and I do a loop, and it can be essentially a loop like this that's a square box. It can be any other kind of loop, as we'll see in a minute. The overall change in potential around that loop is equal to 0. That's what that says. And this little circle here on the integral sign says we're doing an integral around a closed loop. So let's look at this. As I move this way, I'm really not changing my potential energy, am I? Because I'm going orthogonal to the electric field. As I go up this way, basically I'm dropping in potential energy because these electric field vectors are pushing me along. So my potential energy is dropping, but likely my kinetic energy, the speed, is increasing. As I come back this way, again, I'm going pretty much orthogonal to the electric field until I get here. But then at this point, what happens is I start to go with and gain a little bit of speed because those arrows are pointing along the direction I'm going. Now, let's go and get here. As I move back to this point, now I have to fight the electric field. And any of that potential energy I lost, kinetic energy I gained, is basically being lost as I climb back uphill and gain my potential energy back to 0. It doesn't matter the path I do it. If I basically fight against the electric field, go with the electric field, and then come way out this way and fight against the electric field, overall the change is going to be 0. Doesn't matter the loop. Now, this is kind of an interesting case because essentially what it says is that there will never be electric fields that do what these electric fields seem to do here. Because I can imagine if I extended my diagram that I might have an electric field that looked like that made a loop like that. And what this theorem says is that you will never ever see electric fields that swirl. Why not? This is simple conservation of energy. If I put my point here, essentially, and put a charge here, let's call it Q, and let it go along here, it would continually pick up velocity. It would go faster and faster and faster and be pushed along until it came back here and be going faster than when it started. As it went around for a second loop, it would gain still more speed, so it would just be going round and round and round, getting faster and faster each time. This violates conservation of energy. We can get free power this way if this ever happened. So you never ever see electric fields that do complete loops. And in fact, the vector field that I plotted here for an electric field probably is not a physical one because I didn't think about this when I was generating this graph. So we've considered how to go from an electric field to a potential. What if you want to go back the other way and go from a potential distribution to calculate an electric field? And here we go back to the figure that I opened with showing the electric field, which are these black arrows, and the potential distribution is a contour map of a single point charge. If you look at this, it looks like these arrows are always pointing downhill from the high potential, where the charge is here, Q, pointing away from it, pushing down to less and less potential energy. And since we used an integral to go from electric field to the potential, it seems sort of logical that we might need some kind of derivative to go from the potential to an electric field. And essentially looking at this graph, what we need essentially is a function that points in the direction of maximum change, because these electric fields are always pointing in the direction of maximum change, and it's proportional to the rate of change. In other words, the closer these equipotential lines are together, the longer the arrows are. And it turns out that there is a function that takes derivatives of of potentials, of scalar fields, and turns them into vector fields, and that function is called the gradient. It turns out the gradient gives you the maximum rate of change of a scalar field, or the maximum rate of change in a particular direction. So what I've done to illustrate this idea of gradient is I've used MATLAB to create a scalar field. This is the function I use, so essentially it's just mapping a value that I'm going to call v at every point in x and y. This is the MATLAB script right here that I used to create that. You can type this in and do it yourself fairly easily. And again, we've got basically x and y directions going this way, and the height is essentially the value of v. And I've color-coded this using the color bar command, so you can see that it has a maximum value of 1 and a minimum value of -1. Ones are reds, negative values are blue, and values near 0 are green. So it's pretty intuitive when you look at a graph this way, what direction the maximum change is in. If I were to look at a point right here in the middle, the maximum change is going to be going right uphill. There's no change going sideways on the hill in that direction at all. Again, if I go over here to the side of the hill, the maximum change points right uphill. Again, at this point, uphill, uphill. There's no change in the potential energy as I go around a contour of the hill, as I essentially move along these lines right here. At that point, the potential is not changing. So you can see from this, when I plot a scalar field in this fashion, it's fairly easy just by eye to determine the direction of maximum change. You just think about walking up or down a hill, because essentially the potential energy due to gravity or your mass in a gravitational field is a scalar field. And it doesn't really matter what the scalar field is. We're working in terms of voltage, which happens to be quite hard to visualize because we don't interact with voltage as much as human beings, at least if we're careful, and if we do, it's a sort of a bad thing. But instead of voltage, we can think of basically the pressure of the air. We can think of a distribution of temperature, which you would be doing if you were a mechanical engineer. All of these are examples of scalar fields where we can map a value to every point in space. So if this was pressure, you would see a high pressure here, a low pressure here, and you would think that winds would go from high pressure outward into the low pressure. If it was temperature, you'd think of a hot area and a cold area and heat flow. Let's look at exactly the same scalar function in x and y in a different way. I'm going to plot it as a contour map. Again, you're familiar with this if you've looked at any kind of geological maps or anything like that. And the MATLAB function I used to create this is here. Again, we've got a high area here with a value of 1, a low area there which is blue with a value of -1. And now we can introduce the gradient function, which essentially is this function right here. If this is my scalar field, the potential is a function of x, y. The gradient is given by the derivative along x in the x direction plus the derivative along y in the y direction plus the derivative along z in the z direction. So let's take a look at our contour map and see what this is. Obviously, I'm not working in 3 dimensions, I'm working in 2 dimensions because of the limitations of technology, so we're going to ignore that component for the time being. And let's make clear that we're going to call this x and we're going to call this y, and we're looking top down and looking at the value of the voltage in x and y here. Let's take a point right on the origin right here. What's the rate of change of the scalar field in x? Well, right at the origin, you can in fact see that there is no change, that things are changing in the y direction, and the change in a positive direction goes that way, but there's no change at all along the x-axis. So at this point, this gradient essentially gives us a vector in the y direction, and this vector is proportional to the rate of change of this function at this point in space. What happens if we take a point over here, for example? Again, here what we see is the change is in the x direction, positive change going in that way, but there's no change in the y direction. So essentially what this gradient is doing is at any point in space we calculate the derivative. If we choose a point here, we can see that there's both a change in the y direction because the potential lines are increasing that way. We also have a change in that direction. So the overall value of the gradient is going to give us both an x component and a y component, and is going to point in this direction. While in this case it only had a y component pointing that way, and over here it only had an x component pointing that way. So you can see sort of intuitively what the gradient does, is it gives you a vector field that points in the direction of maximum rate of change of a scalar field. Now, we don't like to write things out really long like this expression right here. because our hands would get really tired. So what people have done is they've created something called a del operator, and del is equal to this expression right here, and we represent it by an upside down triangle with an arrow above it. And essentially the way we then write things is like this. We'll write del v, and that's actually equal to this entire expression out here. But the way you'll see it written in books is that. So whenever you see the gradient, del v, it really means you've got three completely separate equations, one in the x, one in the y, one in the z, and each of those expressions is the x, y, or z derivative of that scalar field. Okay, we're almost done now. So we know the gradient gives us the maximum rate of change of a scalar field, and now I can go ahead and plot essentially the gradient on top of the other function, which I've done right here. I've essentially used the gradient command in MATLAB and the quiver command to plot both a scalar field and a vector field on top of one another. We know that the gradient of a scalar field creates a vector field, and each vector points in the direction of maximum rate of change of the scalar field, and the magnitude of the vectors is essentially the rate of change. From this, it's easy to calculate the electric field from a scalar potential distribution by just taking the negative of the gradient. Now, why do we take the negative of the gradient? Because in charge, things point away from the charge, and when we take a gradient, we're pointing uphill rather than downhill. So this negative just means that we're going to switch the direction of all those vectors around and point downhill rather than uphill, because that's the convention. And remember, whenever you see this del, this is the del operator, and we'll see that del as we do other things called divergence and curl later on. But this is a shorthand notation that can be translated, as we saw previously, into a much longer expression. So let's get into a little practicalities to end. The gradient actually turns out to generally be an easier way to calculate the electric field, because if I think about an integral in basically along a line charge, some path, this line or distribution of charge is essentially in three-dimensional space. I'm going to integrate along a path in three-dimensional space here, and not only do I have to consider three dimensions when doing this integration, I essentially have to think of a vector in the numerator and a term that has a cube in the denominator. This is probably a really, really nasty integral to do, and is not something I want to attempt analytically unless I was very, very fond of mathematical masturbation. So a much easier way to do this is to calculate the potential at every point in space, because notice now I'm calculating a number rather than a vector. I don't have a cubic term in the denominator, I just have a first-order term. And once I calculate that potential using superposition, I can then simply take the gradient of that function, and it's very easy to do derivatives compared to doing integrals, and that gives me the electric field. So rather than calculating this directly, a lot of times it's much easier to calculate the potential and then take a derivative to go up and get your electric field. And you'll see many times this is how computations are done, or calculations are done, either on the computer or if you do them analytically.